Alright, now we're going to move on to section 4.6, which is related rates. Now, I want to point out, if there are two things that you become really, really good at this year to carry on through next year, one of those, I hope, is related rates. Related rates is just the rate of change of two or more variables that are changing with respect to time. So we're going to be doing implicit differentiation on all of the variables with respect to time. Some guidelines to follow. It really helps to identify all of the given quantities and the quantities that we want to determine. Sometimes those are rates, sometimes they are constants. Make a sketch if possible. It's not always possible to draw a good sketch, but make a sketch if possible and label the quantities. Write an equation involving the variables whose rates of change are either given or are able to be determined. Then use the chain rule, implicitly differentiate both sides of the equation with respect to time. After completing step 3, substitute in the resulting equation all known values for the variables and their rates of change and solve for the missing variable or rate of change. It's really important that you substitute in after you do the differentiation. Okay, so let's look at an example. We'll start out simple. So a pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? So first, here's a lovely image, so you can have a picture in your head of what this actually looks like, because this is a real phenomenon. And here is a lovely sound effect, so that you can actually hear it as well. That was fantastic. Okay, so now let's get to the actual math. So if we draw a circle, I have some radius, and I know that my relationship is area equals pi r squared. Now, what values do I know? The radius of the outer ripple is increasing at a constant rate of 1 foot per second. So what is increasing? The rate of change of the radius. So I know dr dt is 1 foot per second. It's also important that I put the units in there so I know that everything is in terms of the correct units. When the radius is 4 feet, at what rate is the total area changing? So I'm trying to find dA dt, and I know r equals 4. Okay, so I identified the given quantities and the quantities to be determined. I drew a sketch. I wrote an equation involving the variables. Now I'm going to use the chain rule to do implicit differentiation. So take the derivative of both sides. The derivative of the area with respect to time is dA dt equals 2 pi r dr dt. So remember, now everything is with respect to t, so everything is getting implicitly differentiated. Now that was step 3, so now step 4, after completing step 3, I can substitute in the known quantities. So dA dt is 2 pi times 4 times 1, so I know dA dt is going to be 8 pi feet squared per second. Now this is a word problem, so we also want to answer in the context. So area is growing at 8 pi feet squared per second. This is a related rates problem. Let's look at the next one. So a 10-foot long ladder is leaning against a vertical wall. The foot of the ladder is being pulled away from the wall at a constant rate of 2 feet per second. When the ladder is exactly 8 feet from the wall, how fast is the top of the ladder sliding down the wall? Okay, so let's first draw our picture. So if I call this X, and I call this Y, and I call this Z, I'm going to assume that this is a straight wall, and I know the foot of the ladder is being pulled away from the wall. So this is moving this direction, therefore this end is moving down the wall. So when the ladder is exactly 8 feet from the wall, how fast is the top of the ladder sliding down the wall? So the top of the ladder is going to be represented by Y. So if we're trying to find how fast is that falling, we're trying to find dy dt. X is the bottom of the ladder. Dx dt equals 2. X is 8 feet, and sorry, this was feet per second. Z is 10 feet. And what's dz dt? Well, z is the length of the ladder. So is the length of the ladder changing at all? No. So dz dt is 0. So now I want you to try to come up with a relationship between the three variables, and then try to use related rates to solve for dy dt. Pause the video, unpause when you're ready to check your work, or if you get stuck. Alright, so we should end up with the ladder sliding down the wall at 8/3 feet per second. So how do we come up with that? Well, we already drew the picture and found our information. Now, the one thing that we didn't do previously was recognize that y is going to equal 6 when x is 8 and z is 10. Now, if you didn't recognize that this was a 6, 8, 10 triangle, you could use the Pythagorean Theorem to find the missing side of the triangle when the other two variables are constant. It's okay to do that. That's not jumping ahead to step 4 yet, because this equation doesn't involve rates yet. So that's how we know y is going to be 6. We still need to find dy dt. So now we are going to use the Pythagorean Theorem, though, because whenever we have a right triangle, the relationship between all three sides, or the simplest relationship, is the Pythagorean Theorem. So I know x squared plus y squared is z squared. So now I can take the derivative of this, and I get 2x dx dt plus 2y dy dt equals 2z dz dt. Since everything has a factor of 2, I can just divide by 2. So I got rid of the 2's. Now x is 8 and dx dt is 2. Y is 6. I don't know dy dt. Z is 10 and dz dt is 0. So now I simplify and solve for dy dt, and I get dy dt is negative 8/3 feet per second. So the negative is because it's going down the wall. When we're doing these related rates, you want to pay attention to whether you get a positive or negative answer, but understand how does that apply to the context of the problem. So when we write our answer in a sentence, the ladder is sliding down the wall at 8/3 feet per second. We don't need to include the negative there. Next one. Water is pumped from a cone-shaped reservoir. The vertex is pointed down 10 feet in diameter and 10 feet deep at a constant rate of 3 feet cubed per minute. How fast is the water level falling when the depth of the water is 6 feet? So here we have cone filled with water, and So the main equation we're going to use, you may or not remember this is from geometry. What is the volume of a cone? Volume is 1/3 pi r squared times h. Okay, so what do I know to start? Well, I know dV dt is 3 feet cubed per minute. What am I trying to find? I'm trying to find dH dt. I know h is 6 when I'm trying to find dH dt. Now the trick to this problem is, notice I have a v, I have an r, and I have an h. Sometimes that's going to be okay, but we don't know dr dt. So instead of trying to find dr dt, since I don't know dH dt, in this case basically what we want to recognize is there are two variables that we do not know the rate of change of. So we need to substitute in for one of those variables. So I need to find a relationship between h and between r so that I can substitute into this volume equation for one of those variables. In this case, I know that I want to substitute in for the r because I'm trying to find dH dt and I know h. So what's a relationship between h and r? Well, that's where the 10 feet in diameter and 10 feet deep are going to come into play. So if we think about a cross section to the cone, I'm going to end up with triangles, and I know that this is 5 and this is 10. So I know a relationship between r and h, and that is r is going to be half of h, because no matter where I am in this cone, I'm always going to have the same similar triangle. So the relationship between r, or the ratio between r and h, is always going to be the same. Now I can substitute that into this volume equation. So instead I can say volume equals 1/3 pi times 1/2 h squared times h. And now if I simplify, we end up with volume equals 1/2 squared is 1/4. 1/4 times 1/3 is going to be 1/12. I'm going to say pi 12ths h cubed. So now I want you to pause the video here and try to do the rest of the problem to solve for dH dt. Okay, so we should end up with the water level is falling at 1/3 pi feet per minute. So once we had v equals pi 12ths h cubed, we can take the derivative with respect to t, so the derivative of v is dv dt equals the derivative of pi 12ths h cubed is pi 4ths h squared times dH dt. Substitute in 3 for dv dt and 6 for h, and then just isolate the dH dt, and I get 1/3 pi. Now again, the trick here is if you have more than two variables and you only know the rate of one of them, you can't find the rate of the other without knowing two of them, so you need to find some way to substitute in, or some relationship between two of the variables, so you can rewrite the equation in terms of just two variables instead of three. Alright, next one. A boat is pulled into a dock via a rope with one end attached to the bow of a boat and the other end held by a man standing 6 feet above the bow of the boat. If the man pulls the rope at a constant rate of 2 feet per second, how fast is the boat moving toward the dock when 10 feet of rope is out? So I want you to try and do this one yourself. This is going to be a right triangle if you're trying to visualize the picture. There's going to be a right triangle involved, so it's going to be very similar to what we did in number 2. The video here is going to stop, and we'll go on to part 2 to come up with, or to show you the answer. So there will be a part 2, go to part 2. But first solve on your own.